Engineering Made Easy. I am Lalit Vasist. In my previous video, I discussed what is a signal and also very interesting daily life examples of signals. So now in this lecture, I will tell you different types of standard signals. These standard signals are also known as singularity functions. So first of all, let me tell you what are these standard signals. Actually, standard signals, also called as singularity functions, are the signal that are realizable in the laboratory environment. One very interesting thing about standard signals is that these signals can be obtained from one another by successive differentiation or integration. I have also written this thing here, that these standard signals are realizable in the laboratory environment and can be obtained from one another by successive differentiation or integration. How these can be obtained by integration or differentiation, we will see it later in this video. So we will now discuss here some standard signals like step signal, ramp signal, impulse signal, unit doublet signal, sinusoidal, exponential, and at last the gate signal. Okay, so let's discuss each of these signals one by one. So first of all, let's start with the step signal. Here I have written step signal. Mathematically, we can define a step signal as here I have written it. Okay, we can define it as FST. S stands for step. Since it is a function of time, so I have written here t. So f of t is equals to 0 for t less than 0. For all the values of time which are less than 0, or you can say negative values of t, and its value is equals to k. Here k is nothing but the amplitude of the step signal, which is a constant value. So for t greater than 0 values or positive values of t, the value of the step signal is constant, equals to k. Okay, so here I have drawn how a step signal look like. So this is the diagram of a step signal. Here it is the step signal. As you can see that its value is 0 for all the values of time lesser than 0. Okay, in the negative time axis its value is 0, it doesn't exist. But for positive values of time t greater than 0, the value of a step signal is a constant value k. Since its shape is like a step, it is having a shape of a step, so it is called a step signal. One thing that you should keep in mind, that at t equals to 0 it is not defined, it is undefined at t equals to 0, but it is defined at other values of t except 0. Okay, now so this was the step signal. Now we will see the unit step signal. So what is a unit step signal? If we put the value of k equals to 1 here, k is any constant, so let's take k equals to 1, or you can say the unit value. Unit means 1. So if unit value is taken for k, then it will be called as unit step signal. It's pretty simple. So it is denoted by u of t. It is also a function of time, so it is a unit step signal. So we can easily define the unit step signal in this case. Just change the value of k to 1. So u of t, unit step signal, is equals to 0 for t less than 0, as you can see here also. For less than 0 it is 0, and for t greater than 0 its value is 1. Okay, let's now discuss what happens when we shift this signal on the time axis. So now we are going to shift this signal on the time axis. We will shift each of these signals, unit step signal and the step signal, one by one on the time axis. See here, as you can see here we have represented a graph in time and between time and the signal, step signal. So it has been shifted, or we can say delayed by a constant value a. Since it has been shifted to the right side by a constant value k, so we say that since here the time is increasing in the right direction and time is of lesser values in the left direction, so we say that it has been delayed. Okay, since here, suppose here it is t equals to 0, it is 1, 2, 3, so it is being delayed in time as we move in the right direction, so delayed by a. So we represent this signal as f of s t minus a if it is delayed by a constant value a. Similarly, this step signal has been delayed by a constant value minus a, or you can say a value of a on the left side. So it is called advanced by a, since these values of time in the left side comes before than the values of time in the right side. So we say that it has been advanced by a constant value a. So this is a shifting by a. So we write it as fs t plus a, since fs t minus, like this, t minus of minus a, since this is negative value, so it becomes t plus a here. So f of t plus a, it's very simple. Okay, now we can define these signals, these time shifted signals, in mathematical form easily, like fs t minus a, the delayed by a signal, can be represented as its value is 0 for t less than a, and its value is k for all the values of t greater than a. As you can see here, it's for less than values of t less than a, it is 0. Values of t less than a, it is 0 here, but for values of t greater than a, it is equals to a constant value k. Similarly, for the signals which has been advanced by a constant value a, we can define that signal as fs t plus a. Its value is equals to 0 for the values of t less than minus a, and for t greater than minus a, it is k. As you can see it from this diagram, its value is k for t less than minus, so for t greater than minus a, and it is 0 for all the values of t which are less than minus a. So this is the shifted signal, okay, which is advanced in time by constant value a. Now we will look at another kind of signal, another standard signal known as ramp signal. So ramp signal can be defined mathematically as fr. Here r stands for the ramp, so fr of t is equals to 0 for t less than 0, and its value is kt for values of t greater than 0, greater than equals to 0. Here k is nothing but the slope of the ramp signal. Now I will show you the diagram or the graph of the ramp signal. Here you can see this is the graph of ramp signal, okay, between time and this is the ramp signal. So you can see the shape of this ramp signal is like ramp, okay, having some slant, making an angle of theta with the positive direction of x-axis. So this, because of this shape of ramp, it is called ramp signal. Since it is making angle theta with this positive direction of x-axis, so we can find the slope of this straight line, of this line. Tan theta is equals to slope, and we denote this slope by k. As I told you that in the mathematical expression, the k was the slope of the curve, so it can be defined like this. But if we take the value of k equals to 1, then we will say that the slope of this is equals to 1. So tan theta would be equals to 1. So from that, theta is equals to 45 degrees. So here in this case, if slope is 1, k is equals to 1, then we will say that it is the unit ramp signal in this case. So unit ramp signal has a slope of 1. Okay, it has been plotted here, making an angle of 45 degree here, and k is 1. So it is written as RT. Okay, we can see here by this its mathematical form that RT ramp signal, unit ramp signal, is equals to 0 for values of t less than 0. As you can see here, it is having 0 value for negative values of t, and its value is t. Since in that case it was kt in case of ramp when it was not a unit, so it was kt. Since here I have taken k equals to 1, so its value is t for t greater than 0. So for t greater than 0, it is a line y equals to t. Okay, so this was ramp signal, unit ramp. Now we will see the shifted version of this ramp signal, as we have seen it in case of unit signal also. Okay, so how does it look like? Look at this. This signal, this plot has been shifted to a constant value of a, okay, in the right direction. So it is denoted as FRT minus a. All the things are same as was in case of unit step signal. So it has been just shifted. That signal has been, it was the original shape here, and it has been shifted by a constant value a in the positive direction. Okay, right side. So we can write it mathematically as FRT minus a is equals to 0 for t less than a. Okay, its value is 0 for the values of t less than a, and its value is kt minus a for the values of t greater than equals to a. So the value of t is, if it is greater than a, then this is the equation of this line is kt minus a. But we can also draw the above graph by another approach. Here I am going to tell you how did I get this equation. Okay, since we know that the equation of a straight line passing through x1 comma y1, any two points, any two coordinates, one coordinate x1 comma y1, and having slope m is given as y minus y1 is equals to m x minus x1. These x1 and y1 are the points through which the line is passing, and m is the slope. So, okay, slope of the line. So okay, so y is equals to kt minus a. So in this case, okay, y equals to kt minus a, we are proving that by this approach how to get this equation. So here m is equals to k. If you see this, if you compare this with these two, then you can see that k is equals to m here, and x1 is a here, x1 is a here, and y1 is 0, as y minus y1 is, in this case it is 0. So we can write it as y minus okay, so we can write it as y minus 0 is equals to k x minus a. So y is equals to k x minus a. Okay, so this is the equation. So we can write x by t in this x-axis. On the x-axis we have x t here, so we write it as y is equals to k t minus a. So we got it, k t minus a. This is the equation of this. Okay, now let's come to another kind of signal called as impulse signal. Impulse signal is also called as direct delta signal. We can write it as f delta t equals to 0 for t not equals to 0, and its value is equals to its value is equals to a for t equals to 0. Here, what is a? A is the area of the impulse signal. It is also known as the strength of the impulse. A is also known as strength of the impulse. Let's understand it with the help of a graph. This is the graph of the impulse signal. As you can see here, how it has been drawn, that its value is 0 for all the values of t which are not 0. So only at t equals to 0 it has value a. Okay, at all other points except t equals to 0 it doesn't exist. Okay, and all these values, either negative or positive or negative, its value is 0. Only at 0 it has value a. So if the value of a, if the area of the impulse signal is 1, we are taking a as 1, then it would be called as a unit impulse signal. Okay, so unit impulse signal can be defined as delta t. So delta t is equals to 0 for t not equals to 0, and its value is 1 at t equals to 0. Okay, its value is 1 at t equals to 0. So let's write here 0. Okay, so we can define the area of the unit impulse signal like this. This a value can be defined as integration from minus infinity to infinity delta t dt. So we have defined it for all the values of t from minus infinity to infinity with respect to time. So it is equals to 1. So a is always equals to 1 for unit impulse signal. You can understand it by this example also, this graph also, how it is 1. Let's draw here two I have drawn here two rectangular shapes. Here it is a on the x-axis, and on the y-axis its height is 1 by a. So if I multiply this blue rectangle, then its area will be 1 by a into a equals to 1. Similarly, in this case, the area of this orange rectangle would be 1 by b into b equals to 1. Okay, so a is equals to 1 in all these in both these cases. So area of these both rectangles is 1 each. Since you can see here that as I decrease the value of a, so the value of 1 by a will increase. Therefore a into 1 by a will remain same, always equals to 1. Okay, so now let's see the shifted impulse f delta t minus a, denoted by a. I am here shifting it on the positive x-axis in the right side. So its value is 0 for t not equals to a, and its value is a for t equals to a. As you can see here in this diagram, this is the shifted impulse signal, that its value at a t equals to a is equals to a, but at all the values of t except a, it is not defined. It is 0. So it has been shifted from here to here, so it is only defined at a. It is all has only value at value of a at t equals to a. Okay, at other points it is 0. So this is f of t minus a, shifted impulse. Okay, I think you got it. Now we will see some interesting results about some mathematical results about these signals that we have discussed. Let's look at this. You can see here, this is the unit ramp signal. This unit ramp signal r of t can be written as TUT. Here, what is UT? These are some interesting results, some useful results. So ramp signal can be written as TUT. It is the unit ramp and the unit step. So in the same way, for the shifted case, when we shifted by a, so you can write RT minus a equals to t minus a ut minus a. Just replace the t with t minus a in this equation, so we get this. Similarly, since this was the case of unit ramp, so we can write at FR, this ramp signal, not unit case, general ramp signal, FRT is equals to, since we know that FRT is KRT, so we have seen this, that FRT is equals to K times of RT. Since K was 1 in case of unit ramp, so you can see here K is same here, and RT is nothing but TUT. Okay, so FRT is KTUT. Now see some examples, see some results for the shifted ramp. FRT minus a shifted by a is equals to KRT minus a. From this you can see K replace this t by t minus a is equals to KRT minus a. So K t minus a ut minus a. Since R t minus a we have defined it as this, so replace the value of t minus a from here. Okay, t minus a, put this value here. Now we will see some more results. As I already initially told you that these standard signals have a very interesting property, that these can be obtained from one another by successive differentiation or integration. So let's see how does this happen. The differentiation of a step signal with respect to time can give us the impulse signal. Okay, and if we see the reverse action, then we can say that if I integrate this, then I will get this. So integration of this impulse signal with respect to time will give me the step signal back. Similarly, there is a relation. This is the relation between the impulse and a step. Now here we will see the relationship between the ramp and step. So if I differentiate with respect to time the ramp signal, so I will get the step signal. And in the reverse action, if I integrate this, I will get this ramp. So integrated with respect to time, you will get the ramp signal back. So these similar results can be obtained for the unit cases of the signals. So differentiation of unit step signal gives you the impulse signal, and integration of impulse signal gives you the unit step signal. Similarly, ramp signals differentiation with respect to time will give you the unit step signal, and its integration of this unit step will give you the unit ramp signal. Okay, now we will see another example, another type of signal, a standard signal, which is called as unit doublet signal. Okay, so what is a unit doublet signal? Let's first of all start with the mathematical interpretation of it, how to define it. So it is defined, it is denoted by delta dash t. You know, delta t is the symbol of impulse signal. So dash means differentiation. So delta dash t is equals to d by dt of delta t. So it's just delta dash t. It can be obtained by differentiating the impulse signal with respect to time. Okay, so delta dash t is d by dt of delta t. So this unit doublet signal is equals to plus infinity and minus infinity at t equals to 0, and its value is 0 at when the t is not equals to 0. So you can see the same thing in this diagram, that at t equals to 0, okay, its value is plus infinity and minus infinity, and when t is not equals to 0, okay, it is 0 in all these cases. Okay, so now see the time shifted unit doublet signal. So this is the graph of time shifted unit doublet signal. Okay, so it's, you can see here it has been shifted by a constant value a on the right side. So it has been delayed on the time by a. Okay, so it is denoted by delta dash. Delta dash stands for the unit doublet, delta dash t minus a, shifted by a. So you can see here that for this shifted signal, delta dash t minus a is equals to plus infinity and minus infinity at t equals to a. Okay, at t equals to a, it has values of plus infinity and minus infinity. That's right here, plus infinity and minus infinity. Okay, at t equals to a, but for t not equals to a, it is 0. Since I told you that by differentiation of this impulse signal, I get this unit doublet signal. So we can say that if I integrate this unit doublet signal, then I will get back this impulse signal. Okay, this is reversible. Now we will discuss another kind of signal called exponential signal, very important signal. So exponential signal can be defined as f of t is equals to 0 for t less than equals to 0. Okay, and its value is equals to k e raised to the power minus at for t greater than equals to 0. Okay, so what is k here? K and a are the real constants. This k and a are the real constants. So this is the graph of this exponential signal, this, okay, between time, and this is the graph. Okay, so it is decreasing. Okay, you can see it is exponential curve. So one important thing about in this case is the time constant. So let's understand what is time constant. You can see here that this has been denoted by, this time constant is tau, has been denoted by 1 by a. So this time constant is 1 by a. So what is time constant? Let me define this time constant first, then we will see this graph back again. This time constant is the time taken to reach 63.2% of the total change from initial to final. Okay, what does this mean? Reaching to 63.2% of the total change from initial to final. So look at this. This is the initial stage, this is the time 0. So this is decreasing with time. So when it has decreased to 63.2%, okay, this has been decreased from this value k to this value, so decreased by 63.2. so this remaining will be, so at this height is 0.368 k. Okay, so this is the point which is called the time constant. Its value is equals to 1 by 8. Okay, I think it's clear. So this was the exponential signal. Now let's come to another important signal known as sinusoidal signal. So the sinusoidal signal is defined as f of t equals to 0 for t less than 0, and it's equals to Vm sine omega t for t greater than equals to 0. Here Vm is the peak amplitude or the maximum value of the sinusoidal signal, and omega is nothing but the angular frequency, and its units are radian per second. So here is the graph of this sinusoidal signal. You can see it. This is the shape, and here it is 0, pi, 2 pi. So it cuts the x-axis, or its value is 0 at n pi, at 0, pi, 2 pi, 3 pi, etc. And Vm is the maximum value, okay, of this signal. So this is also very important signal. Now let's see another type of signal which is very important signal. It is called gate signal. So this gate signal is defined as g of t. Here g a b, here you can see ab means the interval of this gate signal. These a and b are the constants on the time axis, so this defines the interval that it is between a and b. So g of t is equals to ut minus a minus ut minus b. So this u denotes the unit step signal. We have seen them. Ut minus a means the unit step signal shifted by a, and this unit step signal shifted by b. A and b are constants. So see here the graph of ut minus a. We have seen them earlier. It has been shifted by constant value a on the right side, and this by b, and its amplitude is 1. Okay, so if I subtract this ut minus b signal from this ut minus a signal, then here I'm taking b greater than a. So here you can see this dotted part. If I subtract this part ut minus b, if here I have let's draw this this ut minus b on this same graph, so b will come somewhere here. If it is greater than a, then it would be like something like this. So if I subtract this from ut minus a, then I will get this gate signal a minus b. It would be of rectangular shape between A and B. So this is the gate signal defined between A and B. So its value is 1. Actually its value is 1 between A and B, and except at other values it is 0. So if I multiply, I'm going to tell you very important property of this gate signal now. If I multiply this gate signal with any signal, then it will become 0 in all the values which are outside this interval A and B, and that signal will be unaffected, or its values will not change within the interval A and within the AB interval. So let's see this. How does this happen? Here I am taking a sinusoidal kind of a graph. So these are the A and B points here. So now I am going to multiply this signal with this gate signal between A and B. It has 1 value and it has 0 values at these points. So if I multiply the corresponding values, multiplying two signals means multiplying the corresponding values, like multiplying this value with this value, multiplying the value at A of this signal with the value of A of this signal. So in this way it is multiplied. So you can see at all the values which are less than A, okay, since it is 0, gate signal is 0 in all the values, for all the values less than A and greater than B. So for this signal also, with values which are less than A and greater than B, the resultant signal, here is the resultant signal product, okay, this is f of t into GAB, okay, GAB of t. So this is 0 in this interval, but in the interval AB it is multiplied with 1 at every value, so it is not changed. So the shape of this curve remains same in this AB interval, okay. If it is negative, then since suppose this is minus 3, let's take an example. If it is minus 3, if minus 3 is multiplied by 1, then it will give minus 3. If plus 1 is multiplied by plus 1, it will give plus 1. So in the same manner, plus and minus, all the values will be retained after multiplication. So this was all about various standard signals. I think you might have enjoyed the video and you will find it very useful. If you want to get more updates about my latest uploaded videos, you can subscribe my channel, Engineering Made Easy. Thank you for watching. Have a nice day.